Okay, welcome. Today we're going to take a look at force problems in 2 dimensions when the forces do not all align with the coordinate axes. And we'll do this by looking at an example problem. So, which I'll introduce by way of a story. So back in 2007, I went to the New York Ren Fair and I saw this guy. He was a slack rope artist and he rode a unicycle on the slack rope and juggled at the same time. There was one point even where he got a audience member or a plant, someone to come up and sit on a little chair on a post that he balanced on his chin. And I don't remember whether he was juggling at the same time as he did that or not, but it was amazing. So, anyway, let's say that you are a slack rope artist and you are going on the your slack rope with your unicycle. And you want to make sure that your slack rope is going to be able to withstand, the forces you're going to subject it to in your show, and get a sense about how large of a force you might put on it. And so we're going to look at a simpler situation where we're not like bouncing up and down on it or anything like that, and we'll take a look at this and see how we might do the analysis for it. So first thing we need to do in any sort of situation here, we're trying to find what the tension on the rope may be. We need to identify the different forces. We need to and start drawing them in first. So we've got tension in this rope, and it could be the same tension in both sides if the angles were the same. We'll see in a moment how this is the case, but it could be that they're different. So I'm going to label this T1 and this T2. So we actually may be interested in 2 different tensions in this problem. And now we want to see what else is acting on this rope. Well, we know that we've got some weight here, but technically speaking, what's going on is that the cyclist here is pushing down on the rope with a normal force, and that from the third law, the normal force on the rope is equal and opposite to the normal force the rope is exerting on the unicyclist. And so if you have your unicyclist on the rope here, they have their weight going down and the normal force on the unicyclist going up. And when we look at the second law with him or her or they or whomever, their normal force up minus their weight will have to be 0 if we're in equilibrium, which for this problem we're going to assume that we are. And so that's going to make it so that this normal force pressed down is the same force as is balancing the unicyclist's weight. If the unicyclist were bouncing or something, then the net force would need to be up, and you would have to have a larger force here. So we'll say for the now that this is equal to the weight of our unicyclist. And so now we take a look at this, and we need to pick a coordinate system. And these things are often angles relative to a horizontal. I'll call this theta 1, and theta 2. And we see that in some sort of general case, nothing is along the same axis, nothing is parallel or anti-parallel to each other, nothing is perpendicular to each other. So there's not really a natural coordinate axis to go with here, where you can reduce multiple things to be 0 for different components. So we may as well pick the traditional sort of xy coordinate system, where positive vertical is y, upward is positive y, and to the right is positive x in the horizontal plane, and we'll go from there. So once we have this, we know that if we want to find these tensions, we are going to have to look at Newton's second law of motion, which is a vector quantity, so we'll need to look at it separately in each coordinate system. So we can do that. Let's go. We're going to have the net force in the x direction equals mass times x acceleration, and we're saying here that we're in equilibrium, so that we're not going to go ahead, we're not going to bounce our rope up and down. But if we were, we get to add that term in. And over in the vertical direction, we also have this. This is our Newton's second law. And before we can go further with that, we need to take a look at all of our forces and break them up into components. It's one of the earliest steps that we're going to do in any problem with more than one dimension, is to break up any vectors into component vectors. That is what's going to make analysis simplest. So we're going to have a T2x and a T2y, a T1x, a T1y. And so if we look in the x direction, our horizontal direction, we've got T2x in the positive x direction and T1x in the negative x direction. So we're representing these here, writing them as magnitudes rather than expressing them as vector quantities. Since they are collinear, we're looking at the components. So they're going to balance each other. So this is our constraint on how the tension relates to the other sides, is that the horizontal components must balance if there's no horizontal acceleration. You start rolling forward, rolling backward, then you get some acceleration, and the tensions change. But they're also dependent upon angles, like we have for our trig relationship. So I'm going to set this up to be connected to the magnitude of the overall tension and our angles. So this is T2 cos theta 2, and then T1 cos theta 1. And I might want to solve for T1 before T2. So I'm going to isolate this, isolate T2 here, so it can be substituted in to any future equation we develop for the vertical components in terms of T1. But we see our relationship between the two here. We expressed this before we've put any numbers in. We can see, oh yes, if the angle for T1 gets bigger, then that's going to make this ratio smaller, and so that's going to make T2 let's see. So that will make T2 have to be smaller compared to T1, and then the reverse will be true. If the angle for T2 gets bigger, then the denominator gets larger, and T1 this ratio becomes bigger, and T2 gets larger. So let's see how this plays out. In the vertical direction, we have both components of tension are vertical, are upward, and that normal force is downward. And I know that my tensions, which I'm looking for, don't have any part in the normal force directly. So I'm going to go ahead and get that on the other side. And we've got T1 sine theta 1 plus T2 sine theta 2 gets to equal all this loveliness. And so we'll take our value for T2 that we solved over here, looking at what was going on in the horizontal direction. And we've got T1 sine theta 1 plus T1 plus T1 cos theta 1 over cos theta 2 times sine theta 2 equals mg in this case. And so then it's T1 times sine theta 1 cos theta 1 plus cos theta cos theta 1 sine theta 2 all over cos theta 2 is mg, and then you get this giant beast of an equation of cos theta 2 mg over sine theta 1 cos theta. So this is cos theta 2 cos theta 2 plus sine theta 2 cos theta 1 in the denominator. And you may have gotten impatient at some point along the way and dumped numbers into this, but I tend to like to keep all of my relationships in terms of variables as long as possible so that we can see the patterns that happen when any of these things get tweaked. And once you have that, we could dump that back into our equation for T2, and we can see that if we do that, then we're going to wind up, let's see. I'll hold off in saying what that ends up being equal because I don't want to do the math on the fly for that. But this is basically our setup for this. Now, if we had this so that these angles were the same, then cos theta 1 and cos theta 2 would just be cos theta, and so T1 and T2 would be the same. So solving this equation in the horizontal direction for Newton's second law would tell us that the tension would be the same on both sides. The vertical parts have to balance the vertical part coming from the unicycle. And that's it for this problem.